what I want to do here is give you an introduction to the many different ways that we can use GPS to observe the Earth system. We think of GPS, or I should say GNSS, so the Global Navigation Satellite System encompasses all the different satellite constellations. GPS we often use to mean all of them, but that's actually just the American satellites. And we think of it as a positioning system, but I want to introduce to you the idea that we can actually use the system to observe many different components of the Earth system. So what I mean is we can do the traditional positioning to observe tectonic deformation, earthquakes, volcano deformation, hydrological loading, where the Earth's crust is pushed down by the weight of water, subsidence due to groundwater extraction, and so on. But we can also observe processes in the Earth's atmosphere, and we can observe other things like sea level change, changes in the depth of snow, vegetation moisture content, and soil moisture content. So let's start by going to the basics of GPS positioning. So GPS works by having a constellation of satellites out there that are sending a signal that a receiver on the ground can use to determine how long that signal took to travel from the satellite to the receiver. And we know the exact location of all of those satellites. If we know how long it took for the signal to travel from the satellite to the receiver, then we can calculate the distance from that satellite to the receiver. If the signal was traveling through a vacuum, then we would be able to just multiply that travel time by the speed of light. It's a little bit more complicated than that, I'll explain. But if we then know exactly where all of those satellites are, and we know the distance to all of those satellites, then for any one satellite, we know that our position must be somewhere on a sphere around that satellite. And so our location must be where all of those spheres intersect. As I said, unfortunately, the signal is not just traveling through a vacuum. So we have to think about the effects of the atmosphere. First off, the signal reaches the ionosphere, which is the top upper layers of the atmosphere. And up there are a lot of free electrons that interfere with the signal and slow it down. Luckily, the amount of interference of those signals is proportional to the wavelength of the carrier signal. So that the GPS signal it's a radio wave, it's an electromagnetic wave. You can think of it as a sinusoidal wave traveling through the atmosphere, and that wave has a frequency. And the delay of that signal as it comes through the atmosphere is proportional to the wavelength, to the frequency of that signal. So the designers of the system very cleverly sent the signal to come on two different carrier waves with different frequencies, and we can then difference them to remove that effect of ionospheric delay. So for positioning, we would just remove the effect. But for other applications, it means that we can use the GPS signal to get a measure of the electron content, the density of those electrons in the ionosphere. And that leads to things like studying ionospheric tsunami. I'll show you more. The next place that the signal hits that has an impact is the lowest areas of the atmosphere, the troposphere. This is where we live, where clouds are, and both dry gases and water vapor in the troposphere can also impact the GPS signal. Unfortunately, there's not an easy way to do that, and that they're not proportional to the wavelength of the signal or anything. But we just estimate this as an additional unknown parameter when we're trying to estimate the position of the receiver. And so for people who care about positioning, that's noise. But for other people who might want to study the atmosphere, then we can use those observations to learn about the amount of water vapor content. Okay. The other uses that I mentioned in the first slide, we can get at those by studying the reflected GPS signals. So if you're worried about only position, then in an ideal world, the signal from the GPS satellite comes straight from the satellite and arrives directly at the receiver. So we get the direct path to that from the satellite to the receiver. However, life is more complicated, and often that signal reflects off other surfaces before arriving at the receiver. We call this multipath. And then you get both constructive and destructive interference of the direct and the reflected paths. The result of that interference is that we see in the signal to noise ratio of the GPS signal, so basically the power of the signal that we receive, we see a sinusoidal wave in the signal to noise ratio as a result of that interference. And that the description of that is very elegant, and it's related to the properties of the reflecting surface. So we have this H naught is the height of the antenna above the reflecting surface. And then the amplitude of that signal and also the phase of that signal are functions of the reflectivity of that surface. So the roughness of the surface and the dielectric constant of that surface. We also have the wavelength of the GPS signal and the elevation angle, which is, we've got all these different satellites in the sky, and this is the angle of the satellite signal intersects with the horizontal. So how does that look in terms of observing the Earth system? Well, here's the top figure shows sort of a normal situation, and we have these sinusoidal oscillations in the signal to noise ratio of the received GPS signal. If we then add a layer of snow, we change the height of the reflecting surface, and so we change that H naught in the equation that I showed before. And so that effectively changes the frequency of the oscillation in the signal to noise ratio data. If we add some vegetation, we basically reduce the power of that reflected signal, and we reduce the amplitude of the signal to noise ratio. If we make the soil wet, it changes the dielectric constant of that surface, and it slightly shifts the phase. So it moves the whole time series in time slightly to the left or right. So that's the theory of the various different ways that we can process the same data, all recorded at a GPS station. Now I'm going to go through some different applications of that, starting with earthquakes and tsunami, and then going into sea level, and then I'll talk about some climate and weather applications, and finally volcanoes. So this is one of my primary areas of interest. This is Sumatra. It was the host of the 2004 Aceh Andaman earthquake, and then a series of great earthquakes after that. And all of these white dots are sugar GPS stations, the Sumatra GPS array. So these are GPS stations that are fixed to bedrock and continuously recording their position. We have the Indian Australian plate is diving down underneath of Sumatra. And during the earthquake cycle, the two plates are stuck together on what we call the cinder megathrust. It's dragging Sumatra down over time. And then in an earthquake, the stress is released and those islands will pop up and move towards the megathrust trench. Here's an example of what GPS time series look like. And I should say Japan has, you almost certainly know, one of the best continuous permanent GPS stations in the world, and has recorded very beautiful data for example, for the 2011 earthquake. And this is what the time series will look like. This is for the 2010 magnitude 7.8 Mentawai earthquake. And you see a sort of what we call static displacement. This is the top plate moving forward and towards the trench in a way that releases several hundred years of stress, and it'll take another few hundred years to move back to the original positions before the earthquake. And then you also see the dynamic shaking, the seismic waves coming through. These are recordings of position every 1 second. We use those data to make figures that look like this. So this is what we call the slip distribution for the 2010 Mentawai earthquake. And so this is the amount of slip on that downgoing surface. So the map is then, the slip is projected to the surface for visualization purposes. And it's the amount of slip that we estimated that caused that earthquake and also tsunami. And then the arrows are the static displacements for the GPS. So that this is how much each GPS station moved during that earthquake. We can build up these slip distributions for many, many different earthquakes when we're interested in things like figuring out where a seismic gap is. So these are all slip distributions for different earthquakes that occurred in Sumatra. And you can see here what we call the Mentawai seismic gap, which is an area that still hasn't ruptured and that we expect will see a great earthquake sometime soon. For a different use of the GPS data, but that still connects with earthquake and tsunami, I want to talk about ionospheric tsunami. So the way to generate an ocean tsunami is that you lift up the seafloor in an earthquake, and that lifts up the water column above it, which creates a gravitational wave. The water wants to go somewhere, so the water flows as a gravitational wave. As that water reaches the coastline, it hits the shallow seafloor, and the friction between the water and the seafloor slow that down, and meaning that water piles up and you get the big tsunami wave that hits the coastline. In that process of lifting up the seafloor and then lifting up the water above it and then lifting up the whole atmospheric column above that, you also generate this gravity wave in the ionosphere. So you cause a tsunami in the electrons in the ionosphere, in that upper layer of the atmosphere. That will travel at the same, it won't cause any troubles for humans, and it won't slow down because it doesn't reach a coastline, so it doesn't experience the same friction as the water. So that ionospheric tsunami wave will actually arrive at the land sooner than the ocean tsunami. And that led us to ask the question, does that mean that we can use information from GPS on these ionospheric tsunami to help in tsunami early warning? And we had a beautiful test example for Sumatra in which there were 2 earthquakes in 2010. The Mentawai earthquake to the south, 7.8, and then another 7.8 earthquake up in the Banyaks. And they're the same magnitude, same year, observed by the same network. But the difference is that the Mentawai one was shallow, and therefore it really lifted up the seafloor and generated a very huge tsunami. Whereas the Banyaks one was deep, and didn't generate very much of a tsunami. So we wanted to look at what was the ionospheric response for that. And what you can see in the top one is the response of the ionosphere for the Mentawai earthquake. And then in this lower graph, you can see the same thing for the Banyaks. And note that the scales for the top one, the y-axis is very different for these two graphs. And you can see a clear ionospheric response for the Mentawai earthquake, the one that did create a big tsunami. And you do not see it for the Banyaks. And this response can be detected much earlier than the tsunami would hit the land. And you can see it in this case, about 8 minutes after the earthquake was generated, we were able to detect the disturbance in the ionosphere for that. It also shows up in these colorful frequency plots. Moving to a different application, sea level. And here, so GPS positioning is useful for sea level studies just because it can be used to observe the changes in the height of the land. But GPS, if the station is near to the coast, it can also be used to observe changes in the height of the sea surface. So here we have the reflected signal off of the sea surface. And what we're interested in is that H factor from the equation I showed earlier. The distance between the antenna and the surface is reflecting the signal, the sea surface. If you change the height of the sea surface, then you're going to change the frequency of those multipath oscillations. And you can basically calculate a periodogram to look at the frequency of those oscillations and use that to deduce the height of the antenna over the sea surface. And it works incredibly well. This is a comparison of a tide gauge shown with the solid line, so an instrument stuck into the water and directly observing the sea level change. And then the colored squares and triangles are the GPS observations. And you can see that these agree really nicely. Also, in terms of measuring the height of the reflecting surface, it can be used for measuring snow depth. This is a study that was done by Christine Lawson. She's pioneered a lot of this work on GPS reflections. And the red dots show basically someone went out in the snow and stuck a stick in the ground and figured out how deep the snow was. And then the blue, and it's nice because it's now continuous, it's not just when someone wants to go and get cold and walk out in the snow, are the GPS observations, again showing really nice agreement. So that's really important for remote environments where you want to be able to study snow depth. We can also use that same technique to study storm surges. If you have a tide gauge to observe a storm surge or also a water tsunami, then that often will get destroyed when the storm surge comes in. GPS, on the other hand, you can have your instrument on top of a building receiving the reflections from the sea surface, and it stays safe during the storm. And what you see here is an example from Typhoon Mangkhut, which hit Hong Kong on the 16th of September 2018. And the red line is for tide gauge, which luckily did not get destroyed in this instance. And then the green dots are from the GPS interferometric reflectometry technique, this technique of using the reflected signals to look at changes in the height of the reflecting surface. The reflection technique can also be used to look at soil moisture, and this is getting at the reflectivity of that surface, and in particular the dielectric constant, and it has an effect on the phase. So you can see in this bottom figure that you slightly shift the oscillations in the signal to noise ratio. And this is an example comparing in situ measurements of soil moisture with estimates from GPS interferometric reflectometry, and you can see really great agreement. And I think what's exciting about this in a kind of innovative new way of thinking about the GPS data is that there's all kinds of stations already installed, in some instances have been running for decades. So you suddenly have a monitor of climate change and other things, even though the stations were maybe installed to study earthquakes. Also related to water, one thing we know is that, so the Earth's crust is elastic. If you put a big weight on the Earth's crust, it will push it down. If you remove that weight, the crust will rebound. And so in areas that have high seasonal rainfall patterns, then if you put the weight of the water on the crust, then it will push the Earth's crust down. And then in the dry season, when you remove that water, the crust will spring back up again. And so if you just look at the position data, just the vertical time series for the GPS, you see these seasonal cycles in the time series that are related to the water load every wet season, and then dry season it moves back up again. These are data from our stations in Myanmar, India, and Bangladesh. This is another example of that, but longer term, and looking at drought in the Western United States, where these more orange dots show uplift of that area due to the fact that there was a severe drought in 2014 in the Western United States. I want you to remember what this figure looks like for 2014, and then take a look at this next figure. And this is vegetation moisture content. So it's in 2014. So it's showing the same drought, but instead of measuring the uplift by removing the weight of the water, it's measuring the reduction in the amplitude of those oscillating signals in the signal to noise ratio data that are measuring vegetated moisture content in the vegetation. We can also look at moisture content in the troposphere in terms of studying weather and climate. And this is an example for Sumatra, where we extract the water vapor content from the GPS and compare it with the index for the Indian monsoon. And you see really nice agreement. So you can use those GPS data to study kind of short-term buildup of big precipitation and storms, all the way through to long-term climate change using those tropospheric delay data. And then my final application is for volcanoes. We can of course use the position data to study inflation and deflation of the volcano, but we can also do something a little bit more creative. This is again work by Christine Larsen, and the idea is basically if you have enough GPS stations around a volcano and that volcano erupts, then when the GPS signal travels through the ash plume, it will be disrupted. The signal to noise ratio data will show that disruption. And if you have enough stations, it means that you can actually estimate the height and density of that volcanic plume. So I hope what I've achieved in this presentation is to show you that we have all these long-running GPS networks around the world, many of which were originally installed either for cadastral purposes, so for defining the national reference frame, or for measuring tectonics and volcanoes. But our understanding of how to process the signals and how to use the data have evolved now to the point that those networks are kind of all environment measuring systems. They can look at climate change, they can look at sea level rise, they can look at droughts and reductions in snow depth, they can look at ionospheric tsunami, they can look at processes of cloud formation and precipitation. So I think that's really exciting. And another exciting thing about it is that because all this is being measured from the same device, from the same system, it allows us to think about the whole Earth system in a more holistic way. We can start thinking about how these different processes connect with each other in many cases. So I thank you for listening. I'm sorry again that I can't hear you. I guess we'll maybe try and fix this again. Now, you're welcome to email me if you have any questions that we can't resolve in this meeting. I also want to advertise that I have some research fellow and PhD positions available, both in using geodesy for sea level rise and also for tectonics. So get in touch if you are interested. Thank you.
Thank you, Emma. So can you hear me? No? It doesn't still work. Okay.
I hope you are able to hear. Okay.
Thank you very much for your
It's a very strange experience not to be able to hear anyone.
Now we'd like to receive a question or comments. So, but the speaker's PC condition is not good, so she cannot hear our voice. So if you have a question or comments, please write down Zoom chat box here. So please. One question. Two. So I hope Emma can read these questions.
So I'll start with the bottom question. Can GPS also be used to detect non-tidal ocean variations? Yes, is the short answer. We can use it. We can look at the loading. So we can study ocean loading signals using GPS. Again, the weight of the ocean water pushing down on the Earth's crust and affecting the vertical positions. We could also have coastal stations that we use for the reflection studies to look at changes in sea surface height. And theoretically, if the river's big enough, we could put a station at the edge of the river too. Yes, to try and get it at river discharge measurements. Brooks' question: if we could improve signal noise by a factor of 2 or add more satellites to improve coverage, what do you think the next frontier is? Gosh, that's a big question. I feel like I might need to think about that one. There are certainly, I think for positioning, we're already at the kind of sub-millimeter position precision levels. We're doing very well already with the positioning techniques, but for these multipath techniques, then the more data we have, the better, certainly. And trying to get coverage from all different angles in the sky is very helpful. Let me think about that one and I'll come back to you. The prospect over the poles, yeah, there's dead spots. So my group actually, we've been installing, the problem is north looking or south looking stations basically see a gap because you don't get satellites flying over the poles. So if you install a station for studying sea level change, for example, and you want to use the reflections, then if you put your station in a nice cove where it's looking north, then all of the reflections come off of the land, and that's not useful anymore. Sorry, it's so difficult to do this without hearing you all. Would there be any difference due to GPS global systems? I guess that question is using with different systems that are not GPS, perhaps. We've had some good luck getting nice results out of GNSS signals, so using the different types of signal. You just have to have a receiver that will actually measure them all. I don't see any more questions,
So
and
any
I
other
guess
question
our
or comment?
time is coming to an end. I'm really sorry again that my audio wasn't working. I don't know what's the problem.
So if you have question or comment, please use Zoom box, chat box. So be.
Okay, great.
Yeah.
Thank you, Monica.
Any other question or comments? No? Okay. So yeah. Again, thank you very much for your lecture.
Thank you, everybody.
Here.
Appreciate the invitation.
Yeah.
Thank you.
Everyone, thank you for coming today. Now we close the AGU plenary lecture. Thank you very much.